All right, everybody, looks like we're ready to get started. Welcome to the Morrison Planetarium. My name is Mary. I'm going to be your presenter today. I'm up in the pilot's booth behind you, waving my arms. Hello, everyone. And today you're here to see our tour of the universe. And this one's pretty fun, I think, because it's the only show we have during the day right now that is completely live. So I'm going to be live flying us through the universe today. Hopefully I don't run us into anything out there in space. And as we fly around the universe, I'll be telling you about some of the things that we see. And we're going to be doing all of this with our OpenSpace software, which is free and open source and lots of real data, and it's very pretty. So I'll tell you more about that in just a second. But before we can fly around the universe safely, I do have a few quick planetarium rules to go over. First of all, please no eating or drinking while you're in the planetarium today. While you're following that first rule, the second rule should be quite easy. Please keep your mask on for the entire show, even once the lights go down, even though I know it's tempting. If you have a cell phone, a camera, a tablet, anything at all that could give off light or a sound, both of those can be very distracting in here, and we don't want to accidentally run into something out in space because I'm distracted, so make sure to keep those all put away during the whole show. And for your safety in this dark theater, but also to make sure we're keeping up our distancing guidelines and everything like that, make sure to stay in your seat throughout the entire program. And once we're done, I'll give you some instructions for how we're going to exit. And last but not least, this can be a very immersive experience. So if you feel any motion sensitivity, any dizziness, anything like that, close your eyes for a few seconds, and that will help your brain to remember that you're just sitting in a chair in a planetarium, not actually flying around in space. So without further ado, go ahead and sit back, relax, and we're going to get started. All right, so we are starting our tour of the universe today, relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And I always like to start out at the International Space Station because this is a nice example of how far humans travel out into space right now. There are a few astronauts on it at any one time. They can fit up to about 6 or so astronauts on the International Space Station. And we've been having people living up there for over 20 years now. But don't worry, it's not just a handful of people that have been stuck up there for many, many years. They swap out every few months or so. And the longest that any one person has lived on the International Space Station was right about a year. And I think this is a nice place to start because in our tour of the universe today, we are going to be covering some really, really vast distances. We're going to see how far our human influence out in space has gone, and we are going to go way, way beyond that. But right now, this is as far as our human influence goes in terms of where human beings go. So you can see the orbit of the International Space Station and that yellow line there as we pull away. And we'll next visit after the International Space Station, we'll see how long in general, or how far in general people have traveled. But for right now, all the humans that are out in space are just a few hundred miles above us, traveling very quickly. Only takes them about 90 minutes to orbit us once. And as we've gotten far enough away, you can see the real location of the ISS right now. We're using OpenSpace today, which, as I mentioned before, is a free open source software. So basically, this is a free planetarium software you can download at home, and this is all real data. So all these pictures we're seeing of the Earth, these are clouds and storms and such that satellites around our planet took today, early this morning. And everything we'll see today is based on actual data and observations that we've made of the places that we're going to visit. But we have a long way to go today, so I'm going to keep us zooming out away from Earth, and I'm going to turn on some more lines here so you can see where the different objects in our solar system are orbiting. And our first visit after the International Space Station is going to be our closest natural neighbor in space. And I say our closest natural neighbor in space because we have a lot of not natural human-made neighbors, our satellites and things that we have going around the Earth. But we also have our natural satellite, the moon. Now, the distances that we're going to cover today are a little bit hard to grasp. We're going to be going distances of millions or even billions of miles and kilometers, and the numbers are going to be very large. So I'm going to try to use a different measurement as we go out to understand how far we've gone. For instance, just now in our trip over to the moon, that took us a few seconds or so. And if we were really traveling around in space, if we were traveling at the speed of light, the fastest speed we know of, it would take us about 1.5 seconds to get to the moon. So our journey with OpenSpace today didn't take too much longer than the real journey would if we were traveling at the speed of light. And I can zoom in a little bit for a second while we're at the moon. Such a pretty picture of the moon that we have here. We're seeing the near side of the moon that we always see from here on Earth with its dark maria and lots of craters on its surface. But I'm not going to stick around here too long and I won't stick around in any one spot too long at all today because I want to be able to take you out as far as we possibly can into the universe. So if the moon, it takes about 1.5 seconds for light to travel there, well then we can actually use that for a distance. We can say that the moon is 1.5 light seconds away from us. So that distance that light can travel in 1.5 seconds, that is the distance in light seconds the moon is away from us. If we want to extend that out to the other objects in our solar system and use light minutes, light hours, and later we'll use light years of distance to think about how far out we're going, that's how we'll gauge all of this. Is if you were traveling at the speed of light, this is how far you could go in that amount of time. And now that I've zoomed out and we can see the planet orbits in our solar system here, you can see the inner orbits right now. We've got Mercury closest to the sun, we got Venus, Earth, and Mars. And then as I zoom farther out, we'll see Jupiter, Saturn, Uranus, and Neptune. But before I get to the outer planets, let's focus for a second on this closest star to us, the sun. Now, how long would it take to get to the sun if we were traveling at the speed of light? Well, at that fastest speed, it would take us roughly 8.5 minutes or so to get to the sun from Earth. So 1.5 seconds to get to the moon, our closest neighbor out here in space, 8.5 minutes to get to the sun. So I like to say that means that if you go outside and you look at the sun, first of all, don't look at the sun. That's very bad for your eyes. But if you did, what you're seeing of the sun, that's how it looked 8.5 minutes ago, not how it looks today or right now. And as we quickly move and zoom out in our solar system, these orbits are getting up to light hours of distance. If I were to bring up the orbit of everyone's, well, I don't know about everyone, but my favorite dwarf planet, Pluto, to go from one side of Pluto's orbit to the other would take us roughly 8 or 9 hours. So it's about 8 light hours roughly to get across a good portion of our solar system here. But Pluto is just one of the many different icy objects that we have far out in our solar system. It's sometimes included in what we call trans-Neptunian objects, which just means objects outside of Neptune. I'm going to turn on some other lines real quick so you can see where a bunch of those are. Whoa, there's so many of them. But you can see a lot of them are out by Pluto. And I like to mention that because often people still ask me why Pluto is no longer called a planet and is instead a dwarf planet. And a really quick reason for that is there's just a lot of stuff that's directly roughly in Pluto's orbit. You can see a lot of these lines are kind of going through where Pluto orbits. And that's the biggest reason why we changed Pluto to a dwarf planet, is because it wasn't big enough to shove all that stuff out of its orbit as it was forming. But still a dwarf planet, still in our solar system, and still is one of my favorite objects to learn about. And we actually have some wonderful pictures of it because of the New Horizons spacecraft, which went out to it just a few years ago. So out here, out to a few light hours of distance. Well, first of all, I don't think I mentioned before that the moon is as far as humans have traveled. So that's as far as we can go when we're talking about our own personal influence of traveling ourselves to other places. But humans have also sent quite a few spacecraft, which should show up there we go. Quite a few spacecraft out into our solar system so far. I've put up these other orange lines here to show how far some of our fastest spacecraft have gone and the spacecraft that we intend to leave our solar system behind. So these are showing the trails of Voyager 1 and 2, Pioneers 10 and 11, and most recently, the New Horizons spacecraft, which visited Pluto just a few years ago and got us some beautiful, beautiful pictures. But even these fastest spacecraft, which the Voyager missions have been going since the 1970s, so over 50 or so years now, roughly, none of these spacecraft have gone much beyond our solar system. I've heard that some people consider them to be outside the solar system. We've been kind of trying to decide if they're outside the solar system or not. But it's a little bit of a tricky question exactly where our solar system ends. Because we've got the planets, we've got the dwarf planets, there's asteroids, there's comets, but there's a lot of little things and influences in our solar system that you could consider our solar system. So having a definite edge is kind of hard to figure out. But if we get far enough out, right around here is when we kind of switch our view so that the sun has its natural brightness. We kind of toned it down before so we could actually see the orbits of the planets and things like that. But now the sun is its natural, normal brightness. And we're getting so far away now that you can see we're starting to fly past some other stars. And the sun is looking like just one of those other stars. Because it is a star, but it's just the star that is closest to us, so it looks very different and very big to us here on Earth. So while we were at light seconds, light minutes, light hours of distance while we were inside of our solar system, for sure, now that we're definitely outside of our solar system, we're up to distances of light years. The closest star to us, Proxima Centauri, which is part of the Alpha Centauri system, which I think if you look at the sun right in the center, I believe Alpha Centauri is that one that's kind of just to its left. It would take us roughly 4 years to travel to Alpha Centauri or Proxima Centauri, traveling at the speed of light. So quite a long distance, even for the closest star to us out here. But we're not done yet with our human influence. While none of our spacecraft have gone out this far, we do have a little bit of influence still as humans out here light years of distance away. I'm going to put up a blue sphere here. That is our radiosphere. So this now is showing us how far any signals we've sent out into space, any radio signals or anything like that that would be strong enough to escape our planet and go out into space, this is how far they could have gone by now, because those radio signals are also traveling at the speed of light. And we've been sending those out for roughly 80 years or so now. So we're out to about probably where we are here. I don't know, we're probably about 100 light years away from the Earth at this point. So you can see this is kind of the edge of our human realm out here in space. So everything else that we're going to see today is still observations. This is stuff that we see with our telescopes. But all this is stuff that just is the light that comes to us that we get to see. Has nothing to do with us sending something out to look at it or sending any sort of signals out there too. And this is a spot where I really like to bring up another object out here in space that we've been learning quite a lot about over the last couple decades. And I'll put up some markers so you can see where they are. These are markers showing us exoplanets, planets that are outside our solar system. So we've got the 8 official planets, we've got our dwarf planets like Pluto, but there's also exoplanets. These are planets that are going around stars that are not the sun, stars outside of our solar system. And so far, we have found over 4,000 of these exoplanets, and we're finding more all the time. And the earliest one, the first one, was found in 1995. So we've only been finding these for a little over 25 or so years now, but we're already up to thousands that we found. And we think there's probably billions out there, around the billions and billions of stars there are out there. And I'm going to toggle those back off, but I am going to leave on our radiosphere, because I'm always curious how long we can keep an eye on it as we zoom farther and farther away. But as we fly past the other stars in our galaxy, we're going to switch from seeing the individual stars to seeing more of an overall model of our Milky Way galaxy. And this is a model, this is not a picture of our galaxy. We're not, as we saw before, we have not sent any spacecraft this far out into space, but we are able to see things this far away. And based on what we see outside of our galaxy, we're able to come up with an idea of what we think our galaxy would look like. So this is a model based on all the data and the images we do have of our universe. And now that we're out here seeing this model of our Milky Way galaxy, we're up to, incredible distances now. So we were at about 100 light years away from Earth when we could see that little tiny dot, which, by the way, do you still see that little tiny dot? Ooh, it's right there, teeny tiny. So that was 100 light years. We're now up to distances of thousands of light years. If we were to travel across the Milky Way galaxy from one end to the other, across the disk of our galaxy here, it would take us roughly 100,000 years if we were traveling at the speed of light, the fastest speed that we know to exist. But we're not done, because our galaxy is only one galaxy out here in the universe. If I keep zooming us out, we're now seeing a lot of other individual dots, and these individual dots are no longer stars. Every single one of these dots is another galaxy with its own billions or sometimes even trillions of stars. And if you're like me, you may be looking at these galaxies and thinking, what are these weird colors? Are there Skittles out there in the universe? No, don't worry. These are not the colors of these galaxies. We've color-coded them based on what different data sets they come from different surveys that scientists and observatories have done. So we've kind of grouped them together based on where they are or when we found them and things like that. And this is indeed a map of all the galaxies that, or most or all of the galaxies. I don't know if we have every single galaxy in this particular map, but this is an actual map of the galaxies that we know where they are, and we've mapped out how far they are away from us. And because of that, it does have kind of a strange shape. So if you look at this map we have of the galaxies in our universe, it looks kind of like an hourglass or a butterfly or something like that. Now, the universe is not shaped like a butterfly, though I do think that would be delightful. This strange gap we see above and below where we're observing from, which appears to be at the center, even though we're not actually at the center of the universe. These strange gaps that we're seeing are because of where we're looking from. Over in those directions, there's a lot of dust and gas and stars and all sorts of stuff in our galaxy, the Milky Way. It's blocking our view, making it hard to see in those directions. So these galaxies that we mapped out here, this isn't even everything that's out there. There's thousands and thousands, probably millions or billions of galaxies more, but we just have trouble seeing them because of our view from here in the Milky Way galaxy. And I do want to make note of something at this point, now that we are really far away. So we were looking at thousands of light years over by the Milky Way. We're up to billions of light years at this point. We're several billion light years away from Earth now. And because of that, it's kind of an interesting phenomenon that we're kind of time traveling in a way, because all these galaxies, all the light from these galaxies, it takes so long to get here that by the time we see this light, and it gets into our telescopes, we're seeing what these objects looked like in the past, not how they look today. So just like I mentioned before, if you were to look at the sun, again, don't look at the sun, but if you were to look at the sun, that's what the sun would have looked like about 8 minutes ago. This is what our universe would have looked like a few billion years ago. And because of that fact, that means that there's only so far that we can go. There is an edge to everything we can see in our universe. And that edge of everything we can see is what we're seeing all over the place here. Now, this is the cosmic microwave background. So this is a map of our universe over 13 billion years ago, as it would look if you could see microwave light. So when you walk outside tonight, you look up at the sky, you're not going to see this up in the sky. Thank goodness. That would scare me if I saw this up in the sky. But if you were able to see with microwave vision, if you could see microwave light, you would be able to see this every single place you look in the sky. And we think of this as kind of the baby picture of our universe. This is light from the universe a few 100,000 years after when the Big Bang would have happened. And the first light that we can see early on in our universe's existence. So, since this baby picture out here is as far as we can go, I can't really take you any farther, but don't worry, I'm not going to abandon you out here in the middle of space. So we're going to take a journey and fly on back home. And make sure to hold on to your seats, because we're going on a journey that if we were really this far away out in space, and if we were really traveling at the speed of light, this would take us about 13.5 billion years. But thankfully, we're in the planetarium, so it should only take us about a minute or so. So here we go, gonna fly home. And as we fly on back home, I want to leave us with one last tidbit. Everything that we've been seeing here today, all of these galaxies, planets, dwarf planets, stars, all the stuff that we've been looking at, cosmic microwave background, that's all the stuff that we can see and we know what it is. There's also dark energy and dark matter, which are both things that we're still trying to figure out exactly what they are or how to see where they are. And dark energy and dark matter combined make up about 97% of our universe. So all this that we can see and map out with visual things that we can look at, it's a very, very small part of everything that's out there in the universe. Now, that may make folks feel kind of weird and small, and I get that, and I feel that way sometimes too, but I also like to think of it as, well, yes, we are rather small, but look at all this that we've already mapped out and seen and discovered, and there's so much more that we get to explore and discover further. So I think that's pretty exciting, and that's how I like to think about it when I think about the vastness of space out here. But with that thought, we're now re-entering our nice little human realm of the universe. We're back inside of the radiosphere, how far our radio signals have gone out into space. So we've got a few tens of light years left to go. We're starting to see our familiar star, the sun, the closest star to us, the center of our solar system. We're seeing the lines of those spacecraft, the fastest spacecraft we've sent out into our solar system. And we're going to head back to the third planet from the sun, the only place in all of this that we have found life at all so far, which is also pretty incredible to think about, I think. And in just a moment, we will be back home. Hooray! So with that, I want to thank you all for joining me today for our tour of the universe. I hope you enjoyed flying through space with me, and I hope you all have a wonderful rest of your day. Thank you for joining us today, and hope to see you another time.